On the first day of class, we defined a vector as a quantity with both magnitude and direction. Yesterday, here 2.5, 3 weeks into class, we learned how to represent a vector graphically. You guys remember yesterday that a vector can be represented by a line segment with an arrow on the end of it. You don't want to put an arrow right here, although I suppose you could. This is typically the way we represent a vector. Now, what's the difference between, let's say, this vector and this vector? Two differences in what they represent. Ethan? Okay, they're going opposite direction. Clearly, one's going to the right, one's going to the left, or one's going east, one's going west. What's the other difference? Yep. Yeah, the length of them, which means the length of the arrows or the line segments that we've got drawn are different, obviously. But, of course, the length of it represents something as well, right? It represents the magnitude of that vector. So one vector is twice as big as the other vector. One might be 20 meters to the right. The other is going to be 10 meters to the left, as the case may be. Does that make sense? All right. Whenever you're trying to add vectors together, we learned yesterday that it's not just a simple matter of saying 1 plus 2 is equal to 3 or 3 plus 4 is equal to 7. When we're adding vectors together in one dimension, you have to pay attention to positives and negatives. But when we're adding vectors together in 2 dimensions, you got to draw a vector diagram. The goal, if you remember from yesterday, is always what? Yep. To get a right angle triangle. Now, you got to draw ultimately a vector diagram that is a right angle triangle. Now, how do we draw a vector diagram? Let's say we have this vector, which let's say is 20 meters to the right. Let's say we have this vector, which is 40 meters downwards. And let's say we have one more vector that's 10 meters to the left. How would we draw a vector diagram here? You guys remember the rules? Or I should say the rule. The goal is to get a right-angled triangle, right? We're not going to get one yet. Okay, that's going to come in a little bit. Right now, we got to focus on that vector diagram in order to get to that right-angled triangle. Jack, do you remember what the rule is here? Yeah, they're going to be drawn front to back, or you could call it head to tail, whatever you want. This would be the, what would you call this? That would be the tail or the back. This would be the head or the front. So if we want to draw this as a vector diagram, we could do this, 20 meters, then we could do 40 meters. Is that okay? Still not done because we got one more vector there, right? But is that okay so far? Okay, then we could do this. Is that okay? What's wrong with that? Head to head, right? We got this one drawn head to tail, which is good. We have this one drawn head to head, which is not good. So we've got a couple of options here, right? In the end, we could draw the other one. You could draw it right here, although it's kind of a little awkward because it kind of comes back upon itself. That would be drawn head to tail. Okay, probably the best place to draw it would be right here, where that one's drawn head to tail. That make sense? So that's how you draw your vector diagram. Draw your line segment with the arrow on the end of it, and then make sure each of those line segments and each of those arrows are drawn so that they're drawn head to tail or front to back. Now, there is one more vector that we draw. Usually we make that a different color or a dotted line or something to distinguish it here. We call it a resultant vector. Where do we draw a resultant vector? From start to finish. This would be, here, let me just erase this one up here. This resultant vector would be drawn start to finish. This would be my start. This would be my finish. So I'm going to draw my resultant vector down here. Ultimately, that's what I would be trying to find, right? That is the sum of the vectors. When I say add the 20 plus the 40 plus the 10, the sum of those, if we're adding vectors, is not 70. The sum of those is whatever that value of r is. Again, we might have a hard time finding the value of r right now because we don't have a right angle triangle. You'll see a little bit later how we make that into a right angle triangle. By the way, there is one more thing that you got to find here as well. Because a resultant vector is a vector, we need both magnitude and direction, right? So we label an angle as well. The angle is always labeled at the start of the vector diagram. So the angle would be labeled up there. Now, right now, that'd be pretty hard to find theta. It'd be pretty hard to find r. Once we get a right angle triangle out of this, then it would be a little bit easier. Make sense? Okay, let's Let's make one a little bit simpler here. Okay, let's say we've got a vector that is 20 meters to the north, and let's say we've got another one that is 10 meters. Actually, let's make it 15 meters to the east. How are we going to draw that? 20 meters? Is that okay? Yeah? How about this one, 15 meters? Is that okay? No? What's wrong with that? That's drawn head to head. We don't want that, right? What about this one, 15 meters? What's wrong with that? Drawn tail to tail. We want to draw on head to tail. So we've got a couple of options here. We could draw it right here. Is that okay? Yeah, that's okay. Okay, that's drawn head to tail. Or we could have drawn it down here. Okay, that's drawn head to tail as well. You're not going to draw in both places, obviously. Pick one. Doesn't really matter which one. Resultant vector is going to be drawn from start to finish. Hey, look what we got. What is it? It's a right-angled triangle. We want to find the value of r, and we would want to find the value of theta as well. Which angle is going to be theta? 1, 2, or 3? It's going to be 1. Always draw the angle at the start. Okay, let's find this. Let's find the value of r and theta since we have that right-angled triangle this time. We're going to say r is equal to what? How do you find r here? Ben? A squared plus b squared is equal to c squared. R is going to be what? A, b, or c? C. So we're going to say c is the square root of a squared plus b squared, or the square root of x squared plus y squared. So it's going to be the square root of 15 squared plus 20 squared. Let's get the value of that on our calculator here. 15 squared plus 20 squared. Oops, that's not what we want. Square root that, and we get a value of 25. Works out to be 25 meters. Now we also need the value of theta, and this is the one that gives people a little bit of a tough time sometimes. Some of you aren't familiar with sine, cosine, tan. If we have adjacent, and that's the 20 is the adjacent side of the triangle, and it's touching the angle, so it's adjacent. We have opposite, that's the one that's not touching. Opposite and adjacent go with which trig function? Tangent. So we're going to say theta is equal to the inverse tan, the second function tan, of opposite over adjacent. Now what's the opposite side? Christian, what's the opposite side here of this triangle? 15. And the adjacent side would be, Christine? 20. So we'd say it's the inverse tan of 15 over 20. On our calculators, make sure you're in degree mode. What's the quick little check to make sure you're in degree mode? Sine 90. What should it equal? 1. If sine 90 equals 1, you're good to go. Okay, make sure when you do a test or a quiz that you are in degree mode here, okay? You will, for a quiz, just, if you're in degree mode right now, you'll be in degree mode for your quiz, right? But for a test, your calculator is going to get cleared, and it's going to go back to radian mode. So you're going to have to remember to switch it back to degree mode. And again, that's your little check. If every time you do a question like this, you go sine 90 first, it becomes a habit, then it becomes just a little reminder for you. Oh, I got to switch it back to degree mode after my calculator's been cleared for a unit test. Okay, so I'm in degree mode here. Sine 90 is equal to 1. Let's say second function tan or inverse tan of 15 divided by 20. Bracket. We got what, 37 degrees? 36.9 degrees, 37 degrees. There it is, right? Now, by rights, I should have a frame of reference here. I should be describing what that's measured from the 37 degrees, because at the end, it's kind of like measuring a position, right? Yesterday, I used this in this example. My position is 1 meter from the front of the room. My position is also 7 meters from the back of the room. Well, I can't just say my position is 1 meter or my position is 7 meters. It has to be from something or relative to something. The angle does as well. We'll deal with that a little bit later on today, though, okay? I don't want to bog you down with finding that frame of reference right now. That'll come later. Okay, just remember that there should be one. So 25 meters at 37 degrees, measured from something that we'll worry about later on. Okay? Okay, I'm going to give you another one here that you're going to do yourself this time at your desk. And then we'll move on and deal with those three vectors. What do we do when we have those three vectors to get that right angle triangle? So let's say we got 25 meters to the south, and we got 50 meters to the west. I want you to add those vectors. Not scalars, right? If I was adding distance, I just get 75 meters because that's a scalar. But if I'm adding displacements and I want a vector out of it, then you got to do the stuff that we just did. Okay, give you a couple minutes to do that, and then we'll check it over, and then we'll move on to three vectors. All right, let's have a look here. 25 meters to the south is going to be represented by a vector that looks like this. 25 meters. We have a line segment with an arrow on the end of it indicating that it's to the south. Our 50 meters to the west should be about twice as long, although I'm not asking you to use a ruler to measure it. It doesn't have to be perfect, but it should be drawn roughly twice as long as the 25 meters is. So it's going to look something like this. How many people drew it like this? How many people drew it like this? Everybody draw it like that? Does it matter? What's 1 plus 2 if we're adding scalars together? 1 plus 2 is 3. What's 2 plus 1? 3. It doesn't matter what order we add scalars together. It also doesn't matter what order we add vectors together. Okay, 25 plus 50 is the same as 50 plus 25. Doesn't really matter. You will get a different angle, but that's just a matter of the frame of reference that we'll deal with a little bit later on, all right? So I'm going to stick with this because that's the way that I do it first. My resultant vector is going to be drawn from start to finish like this. I'm going to find the value of that resultant vector, or at least the magnitude of it, by the Pythagorean theorem, and I'm going to find theta by the tan function. So R is, as somebody said, C squared is equal to A squared plus B squared. R is the value of C, 50 squared plus 25 squared, and then we got to square root that to solve for R. Let's figure that out here. Let's say 50 squared plus 25 squared. Let's square root that now. And we end up getting 55.9 or 56 meters. So 50 plus 25 is 56 meters at some angle. Notice we've drawn the angle at the start of the diagram here. Theta, the angle, is equal to the inverse tan of opposite over adjacent. What's the opposite side here? 25 or 50? 50. And the adjacent side is 25. So we're going to say the inverse tan of 50 over 25. Second function, tan, oh, sorry, you know what we're going to do? Sine 90 equals 1. Okay, we're good to go. The inverse tan of opposite over adjacent, 50 divided by 25, gives me an angle of 63 degrees. Now, if you drew it the other way, which would have been correct, you would have got an angle of 27 degrees. How many people got that? They're both correct. Right? That's like saying I'm 1 meter from the front of the room or I'm 7 meters away from the back of the room. They're both correct. Two different numbers that describe exactly the same thing. The only thing that we're missing in both cases is the frame of reference that we'll deal with later on once we've kind of mastered this stuff. All right? What are we going to do if we have three vectors? Well, if we have three vectors, then we have to use what's called vector components in order to get a right-angled triangle. 25 meters to the north, 20 meters to the east, 30 meters to the north. Well, the vector diagram is going to look something like this. 25 to the north, 20 to the east, one that's slightly shorter here, and then we got 30 meters to the north, something like this. Is that correct? All these vectors are drawn head to tail or front to back. My resultant vector would be drawn from start to finish. That's not a right-angled triangle. We haven't reached our goal yet, but at least we've drawn our first vector diagram. Now what we've got to do is get that right-angled triangle. So now we're going to use these things that we call vector components. X component, Y component. I'll remind you before I do that, that this is your x-axis, and this is your y-axis. So x-axis, okay, you see my hand here, x-axis, and y-axis. Let's go through each of these blue vectors each of these vectors that I'm trying to add together and determine how much of it is x and how much of it is y. Okay, let's look at the 25 meters here. How much of that 25 is x? How much of it is on the x-axis right here? How much of this 25 right here is this way? None. 0, right? So the x component of the 25 is 0. What's the y component of the 25? How much of it's this way? 25 meters, all of it. What about the 20 meters? How much of it is this? How much of it is x component? All of it. 20 meters. How much of it is y component? This. How much of that 20 meters is up or down? None. So we're going to say 0 meters. How much of the 30 meters is x component horizontal? 0. How much of its y component? Up or down? All of it's up, right? So 30 meters is up. Let's add these up. 0 plus 20 plus 0 is 20 meters. 25 plus 0 plus 30 is 55 meters. So far, so good? Now, let's redraw this with these two components. Now, let's say we've got 20 meters to the right. How do we know that was to the right, by the way, as opposed to the left? Because what? Yeah, the arrow's here, but when we just forget about that diagram now, okay, let's look at just the x and y components right here. How do we know that 20? Because what, Jake? Because it's positive, right? So 20 meters to the right. And then how do we know, Megan, that 55 meters is upwards? Because it's positive. Notice I've drawn them front to back again. Hey, look at what we got now if we draw the resultant vector. First of all, we have a right angle triangle, which is our goal, right? It's always our goal is to get the right angle triangle. Notice as well, though, that the resultant vector looks exactly the same as the resultant vector in the first diagram. It's just easier to find now because we've got a right angle triangle. So now we're back to what you guys just did on your own a few minutes ago. Now we're back to finding the value of r and the value of theta by using a little bit of trigonometry. By the way, where would we find theta? Position 1, 2, or 3? Position 1, because we always draw theta at the beginning here. R is going to be equal to the square root of 20 squared plus 55 squared. 20 squared plus 55 squared. Let's square root that. 59 meters. And theta is going to be the inverse tan function of opposite over adjacent. What's the opposite side? Is it 20 or 55? 55. And the adjacent side is 20 because it's the one that's touching the angle. Yeah, we're in degree mode here. So let's say the inverse tan function of 55 divided by 20 gives me 70 degrees. As measured from something that we'll deal with later on. So the sum of these vectors, 25 and 20 and 30, is 59 meters at 70 degrees measured from something. All right? You guys think you can handle the next one? Okay, give the next one a try. Same thing, right? Just remember that there's 4 vectors there. So instead of 1, 2, 3 that we're adding together, there's going to be 1, 2, 3, 4 components. And also, I'll give you a word of caution on this one. Pay attention to signs on this one a little bit more carefully than we had to on the last one. All right, so we've got 10 meters to the east. Let's draw this like this. 15 meters to the south, we're going to draw that so that it's head to tail, right? Head to tail. And we're going to draw that about 1.5 times as long. We've got 12 meters to the west, which is going to be a little bit longer than the 10 meters. It's going to be something like this. And then we got 20 meters to the south, which is going to be about twice as long as the 10 meters. Again, we're not asking you to physically measure the length of those vectors that you're drawing, so it's okay if it's not quite perfect, but you want to be in the general vicinity of the length of it. So let's draw our resultant vector now, which is drawn always from start to finish, like this. And let's do our x and y components. Certainly we don't have a right angled triangle here, but the goal is always to get that right angled triangle. So let's say x components and y components. What's the x component of the first one? Keep in mind, guys, by the way, you could have drawn these in a different order, right? But you would still get the same resultant vector. It would still look the same, even if you had drawn it in a different order. What's the x component of the first one, that 10 meters? How much of that 10 meters is like this? 10 meters. What's the y component of it? How much of it's up and down? 0. How much of that 15 meters is left and right? 0. How much of that 15 meters is up and down? Negative 15, right? Why is it negative 15? Good. Excellent. Negative 15 meters because it's going to the south. Okay, what about the next one, 12 meters? How much of that is left and right? Negative 12 because it's going to the left. How much of it's up and down? 0. How much of that 20 is left and right? 0. How much of that 20 is up and down? Negative 20. So you really have to pay attention to the signs there. 10 plus negative 12 gives me negative 2. Negative 15 plus negative 20 gives me negative 35. So now what we're going to do is redraw this. We're going to say 2 to the left and 35 down. Gives you a resultant vector that looks like this. Okay, again, it looks a lot like the vector that you had as the resultant vector in the original diagram. We're going to solve for, here, let's label these, 2 and 35. Don't worry about the negatives here, by the way. Your arrows are indicating direction now in your diagram. We're going to label this as R, and then we're going to label position 1, 2, or 3 as theta. 1, 2, or 3. 3, right there. We're going to find the value of R by doing the Pythagorean theorem. When we have numbers that are so much different, it's likely that we're going to get a number that's pretty close to the bigger number. So if we go 35 squared plus 2 squared, and then we square root that, we end up getting 35.06, right? Which rounded to 2 digits is still 35. So 35 plus 2 is 35. Theta is equal to the inverse tan of opposite over adjacent. Opposite is what, 2 or 35? 35 is the opposite side because it's not touching the angle, and 2 is your adjacent. We're going to get an angle that's pretty big here. The inverse, sorry, I'm just going to check that here, sine 90. Yeah, we're good. The inverse tan of opposite over adjacent, 35 divided by 2, gives me 87 degrees. Now, anybody do it differently? You get 3 degrees or 2 point something degrees? Yep. Yeah, that's fine. Okay, that means you just drew the 35 first and then the 2, which is absolutely fine. Those are both going to be correct once we learn to use that frame of reference that I was talking about, right? Okay, how many people got that? 35 at 87 or 35 at 2 point, whatever it worked out to be. Okay? Good there? All right, I'm going to give you a worksheet right now, and there's a number of questions on that worksheet, 3 sections. 3 sections. The first section is questions 1 to 5. I'm going to ask you at your desks to work on that first section right now, questions 1 to 5. Okay, let's take a look at question number 1 on your worksheet. This one's pretty straightforward because it's already drawn for you, right? Is it drawn correctly, by the way? Is it drawn correctly? Sure it is. Drawn head to tail or front to back, whatever you want to call it. We just got to draw that resultant vector. When we draw that resultant vector, it's going to look like this. We're going to find the value of R. We're going to find the value of theta as well. Where's theta going to be? Position 1, 2, or 3? Position 1, always drawn at the start there, right? Find the value of R by doing the Pythagorean theorem. Square root of 20 squared plus 10 squared. What do we end up getting there? What is it? 22. We know that that hypotenuse is going to be bigger than the biggest number, right? So if we get a number that's like 16, we know we made a mistake. It has to be bigger than 20. Not always a lot bigger than 20, but it's got to be bigger than the biggest number. So 22 is our number there. Theta is the inverse tan function of opposite over adjacent. What's the opposite side here, the 20 or the 10? The 10. The 10 is not touching the angle, so it's opposite. The 20 is touching the angle, so it's adjacent. Now, that 22 hypotenuse is also touching the angle, but the longest one doesn't count here. Okay, we're talking about opposite and adjacent. We're not looking at the longest one. The longest one's always the hypotenuse. The other one that touches is the adjacent side. So we're going to say the inverse tan function of opposite over adjacent. And what do we get for the angle there? Yep, 27, 37 degrees, 27. Okay, 27 degrees, and we'd express that relative to something that we'll deal with a little bit later. Question number 2 is going to be real similar, so we'll skip that. Number 3 is going to be real similar, so we'll skip that. We'll go to number 4 here. Number 4 involves 3 vectors. Is that vector diagram drawn okay so far? Yeah, it looks to be. Okay, all the vectors are drawn head to tail or front to back. That resultant vector is drawn from start to finish. It's going to look something like this, but we can't find it right now, right? How come? How come we can't find the resultant quite yet? We haven't met our goal yet. What's our goal? To get a right angle triangle. So let's get a right angle triangle, and then we'll see if we can find the value of r there. To get the right angle triangle, we've got to break this up into x components and y components. How much of that first one, that 10 meters, is x component, or how much of it is right or left? All of it. 10 meters is right or left, right? In fact, it's all to the right. How much of that 10 meters is up or down? None of it. How much of that 5 meters is right or left? So how much of that 5 meters is right or left? 0. How much of that 5 meters is up or down? 5 meters, good. How much of that 15 meters is left or right? All of it? Who said that? Okay, all of it. So we're going to say 15 meters here. How much of that 15 meters is up or down? 0. So we're going to say 0 there. Add these up, we get 25 meters. Add this up, we get 5 meters. Now we're going to redraw this 25 meters to the right and 5 meters up. Anybody draw it the other way around? 5 meters, then 25? Anybody do it this way? That's fine. Listen, what you'll find that I usually do is draw x, then y, but there's no good reason for that. That's just more habit than anything else. So if you draw y, then x, that is absolutely fine. Let's draw the resultant vector now, which looks just like the resultant vector that we had in the first diagram, as it should. Label r. Theta is going to be 1, 2, or 3. Position 1, 2, or 3. 1, 1. 1, 2, yeah, it's going to be 2, right? Good. We're going to find the value of r by doing the Pythagorean theorem. 5 squared plus 25 squared. What does that end up being? Is it 25? Yeah, I think it was 25.49 or something, wasn't it? Which, if we just look at the one digit right after the 4, it rounds down to 25. So 25 plus 5 is equal to 25. Theta is equal to the inverse tan function of opposite over adjacent. What's the hypotenuse here? Which one's the hypotenuse? The 25, the 5, or the red one? The red one's the hypotenuse, okay? So we're looking at the 5 and the 25 as opposite and adjacent. Which one is the opposite, the 25 or the 5? The 5, because it's the one, the green one, that's not touching theta. So we're going to say 5 over 25. And what do we get for theta there when we do that? 11 degrees? Somebody else might have gotten 79 degrees, right? If you had drawn it the other way. Good. How many people got that? Okay, good. We're on the right track here, I think. Does anybody need that for another minute before I delete it? No? Okay. Let's take a look at number 5 then. We certainly don't have a right angle triangle here. We've got 1, 2, 3, 4 vectors. There's my resultant, by the way. Nice and short, except it's not a right angle triangle right now. We haven't met our goal. Okay, we got to get to our goal here. Our goal is a right angle triangle, so let's do that. Let's go over here, x and y, to get a right angle triangle. How much of that 8, Christian, how much of that 8 is x component? Pardon me? Good. 0, none. Okay, how much of that 8 is y component? Josh? All of it? 8 meters? Is that right? What is it? Negative 8 meters, because it's 8 meters downwards, right? Okay. What about the 12 meters? How much of that is left or right? All of it? How much of that 12 meters is up and down? 0, none of it. How much of the 10 meters is up and down? 10 meters. Oh, whoops. I should have said left and right, right? You were right. 10 meters is up and down. How much of it's left and right? 0. How much of that 4 meters is left or right? All of it, but it's negative because it's to the left. And none of it, of course, is up or down. 12 plus negative 4 is 8. Negative 8 plus 10 is 2. So we're going to draw 8. And 2 meters. And that's going to give us a resultant that looks like this. R, position 1, 2, 3. Where's theta? Position 1, 2, or 3? Right. Going to be position 3. So we find the value of R by doing square root of 8 squared plus 2 squared. What does that work out to be? What is it? Is it 8? Should be the 2 digits though. 8 point something, I would think. If you look back to your original data, is it 8.0? Okay. 8.2. And theta is the inverse tan function of opposite over adjacent. Which one do we know we're not going to use in the inverse tan function? The 8 to 2 or the red one? The red one because it's the hypotenuse. It's the longest vector of the hypotenuse. Opposite over adjacent, which is opposite? The 8 or the 2? It's the opposite because it's not touching the angle, right? So we're going to say 2 over 8 here. And that's going to be a pretty small angle here. What does it work out to be? 14 degrees. As measured from something, right? How many people got 76 degrees here? Okay, because you do y component, then x component. Is there anything wrong with that? No. 7 meters from the back of the room, 1 meter from the front of the room, whatever, right? A matter of perspective, literally. Is that okay? All right. Listen carefully to what I'm about to say. I will define an angle that's not 0 or 90 degrees. I'll define any other angle, 2 degrees, 37 degrees, 89 degrees, any of those angles in between 1 and 89 as funny angles. 0 is fine, it's not a funny angle. 90 is fine, it's not a funny angle. Any other angle, it's a funny angle. Now, whenever you see one of those funny angles, it's not 0 or 90 degrees. In other words, it's not just x or just y. It's not just right or left or up or down, but it's some kind of combination of those. Right? It's partly up and partly to the right or whatever. Whenever you see a funny angle, I want you to automatically think 5 words. Okay, got it? 5 words. Here are the 5 words. And repeat after me. I don't like funny angles. I don't like funny angles. So when you see a funny angle that's not just this or this, you got to stay in your mind, I don't like funny angles, and I got to get rid of it. Okay? So here's how we're going to do it. We've got to take x and y components of the vector that's at the funny angle. Quick little review of x and y components here. Okay, x and y components of this one. X is 10, y is 0. X is 0, y is 200. X is negative 50, Y is 0. X is 0, Y is, right. The X and Y components of these ones are easy. But what about these ones? What about these ones? Okay, you see these angles here. In the back of your head, you're saying, I don't like funny angles. We've got to get rid of these funny angles by taking X and Y components of these vectors. Now, here's how you do it. You see the angle here as measured from a certain axis, the x-axis to the y-axis. Draw a triangle around it. So there's my angle. Draw a triangle around the angle. You can see that I've done it right there, and you can see that I'm doing it right here. The angle must be inside that triangle. So that means that I'm not going to draw a triangle like this. Don't want to draw a triangle like this. How come? Because the angle's not inside it. Draw the angle, or draw the triangle so that the angle is inside the triangle. How about this? No, that doesn't work because the angle's not inside the triangle. Draw a triangle so that the angle is inside the triangle. Make sure you put those little arrows on the end of it as well, right? This corresponds to the x component, this the y component. This is the x component, this is the y component. Now, remember, I don't like funny angles, so I'm going to try to get rid of the funny angle by replacing it with the x and the y component. How do you think I'm going to find the value of the x component here, given the angle, the funny angle that I don't like, and the magnitude of that vector of 100 meters? Any ideas? Yeah. You guys remember, we talked about this yesterday a little bit. SOHCAHTOA. Most of you are familiar with that. All of you have become a little bit more familiar with that with the last couple of days talking about the tan function. Cosine is adjacent and hypotenuse. Okay, I'm looking for the adjacent side here, the one that's touching the angle, and I've got the hypotenuse. So to find the x component, I'm going to say cosine 30 degrees is equal to adjacent over hypotenuse, or x is going to be equal to 100 cosine 30 degrees. On our calculator, I'm going to go sine 90. Yeah, I'm in degree mode. 100 cosine 30 gives me 86.6025. Now, to find the y component is the opposite side of the triangle. It's the one that's not touching the angle. Opposite, I got the value of the hypotenuse. The opposite and hypotenuse uses the sine function. So I'm going to say sine 30 degrees is equal to opposite over hypotenuse. And when I do that, I'm going to find that I get 50 meters. 100 sine 30 gives me 50 exactly meters. So what you can do now, it is perfectly legitimate now to pretend that doesn't even exist. Understand what I've just done. I've taken one vector that I don't like because it's at a funny angle, and I've replaced it with two other vectors that I do like. Okay, that's like saying you got a club, and you got one person in the club that's just a pain in the butt, and you don't like them. So what do? You kick them out, and you replace them with two other people that are a little bit shorter that you do like. It's easier to deal with those two people you like than it is to deal with that one big guy that you don't like. Here's what I want you to do right now. Look at that 30-degree angle and the 100 meters. Okay, look at it. Look at that 100 meters and the 30-degree angle in the eyes. Look at it in the eyes. And repeat after me. I never want to see you again. Listen, it's gone. It's gone. We don't need this anymore. We don't need this anymore. Okay, this 100 meters is replaced by 86 meters and 50 meters. And we know very well what to do with these vectors when we're trying to add things up, right? If we want to add this 100 meters at 30 degrees to something else, replace it with this and add it to something else, and then it's easy, just like the questions we just worked on, right? Let's take a look at this one. Over here, I see a 30-degree angle. What's your 5-word response to that 30-degree angle? I don't like funny angles. So you got to get rid of it. And how do you get rid of it? Draw a triangle around the 30-degree angle, and then find the value of x and y using SOHCAHTOA. X is, which side of the triangle is that? Opposite. Opposite in hypotenuse is sine. Sine 30 degrees is equal to opposite over hypotenuse. Notice over here, it was cos 30 is equal to x. Here it's sine 30 is equal to x. So each triangle is a little bit different. Okay, that's going to equal 10 meters. We're going to say cosine 30 degrees is equal to adjacent over hypotenuse. 20 times cosine 30. 20 times cosine 30 gives me a value of 17.3205. Now, technically, that's going to be a negative number, but I can sub that in as a negative number later on if I want to. Look at the 20 meters and the 30 degrees. What do you say to it? I never want to see it again. It's gone. That 20 meters is dead to us. We never want to see it again because we've already replaced it with an X and a Y. All right? You've replaced that pain in the butt guy in the club with 2 other shorter people that are much easier to deal with. Okay? Get it? Let's take a look at your worksheet now, the one that you were working on before, and do questions 6 to 10, please. You're going to find that 6, 7, and 8 are very straightforward. Questions 9 and 10, a little bit tougher, because this is when we got the funny angles is in question 9 and 10. See what you can do with those, okay? Number 9. 6, 7, 8, you're probably okay with, right? Number 9 and 10 are the trickier ones. Let's take a look at number 9 here. We've got our vector drawn, 10 meters at 30 degrees. Let's draw our triangle around that 30 degrees. We've got a horizontal line, we've got a vertical line like this. This would be X, this would be Y. We don't like funny angles, right? First thing you think of when you see that vector is, I don't like funny angles. So you want to get rid of it. We want to turn it into a simple X and a simple Y. You want to take that pain in the butt guy in the club, that big guy in the club, replace him with 2 shorter ones, X and Y. So how do we do that? Well, to get the X component of it, we're going to say cosine theta, cosine 30 degrees, is equal to X over 10. Why cosine? Because X is the adjacent side of the triangle, 10 is the hypotenuse. And you remember SOHCAHTOA, cosine is adjacent over hypotenuse. X adjacent over 10 hypotenuse. So X ends up being, well, I'll take the 10 up and multiplying, 10 times cosine 30 ends up giving me 8.66 something. 10 cosine 30, 8.66025. And the Y component, well, the Y component is the opposite side, so we're going to say sine 30 degrees for that. Sine 30 is opposite over hypotenuse, opposite because it's not touching the angle. Y is equal to 10 goes up by multiplying 10 sine 30 degrees. 10 sine 30 ends up being exactly equal to 5.0 meters. Does that make sense? Take a look at the 10 meters at 30 degrees now. What do you say to it? Never want to see again. Right, we're gone. Right, it doesn't exist anymore. Now we've got an X, which is nice and easy to deal with, and a Y, which is nice and easy to deal with, instead of this 10 meters at this funny angle of 30 degrees that we don't like. Yep. Well, that's a good question. That's a good question. Um, would we not do significant digits for this? Yes, we would do significant digits for this, but generally when you see something like this is part of a bigger question. So that's why I left the, 4 or 5 decimal places there, because you probably wouldn't be done at this point normally. Right? I'm just teaching you a tool to deal with something bigger. Okay? All right. For homework, I would like you to do, let's say, up to number 12 on your worksheet. Up to number 12 on your worksheet. So if you finish 9 and 10, that's great. Do 11 and 12. If you finish those in the next 5 minutes, then perfect. No homework tonight. Besides your quiz, of course.